Thank you, Sergey. This is my first Kourovka. I did not know about the existence of this excellent series, which dates back to 65 years. And I must thank the organizers for inviting me, especially Sergey, who has been an unbelievably gracious host. And I do hope we can also reciprocate in some way. Maybe we can have meetings back in India with many of you able to come there. Uh, okay, so today is the day of magnetism, and so my topic of today's talk will be quantum spin liquids and the related concept of topological order. So you can interrupt me if you want to, and I'll be happy to answer questions in the middle of the talk also. Okay, so uh, I have planned this talk in two parts, given that I see a lot of young faces here. Many of you might perhaps not have been familiar with this topic of quantum spin liquids and topological order. So I'll go a little bit pedagogically in the first part by first reminding ourselves what a quantum spin liquid is not. And for that, we have to start with Landau's paradigm. Then we go beyond Landau to understand what is topological order, give some examples. You know many of the examples also. Um, Specifically in topological order, we have the whole universe of quantum spin liquids, which is the focus of today's talk. We'll discuss what kind of theoretical approaches we normally use for understanding such phases of matter. We'll also discuss something more tricky, which is the experimental status, some successes, and what are the big challenges and controversies. I hope to be able to give you a flavor of that, if not a comprehensive view. And finally, I'll give you an example of a problem which is bang in the middle of this kind of an area, which is how to measure properties of a quantum spin liquid. So typically, one of the best things to do would be to measure thermal Hall response. Um, how you really want the low temperature thermal Hall response, because it gives you a very important property of the quantum spin liquid called the chiral central charge of the boundary modes, just like quantum Hall effect, and how it's very challenging to measure it, and so whether we can get some information out from the finite temperature and thermal Hall response. So this is the plan, and I might have to accelerate a little bit towards the end, so please pardon me if I go fast. I know you have to get used to my accent also. Okay, so let's begin with Landau in 1937. Almost everything we see around us is made up of building blocks like electrons, protons, and neutrons. And nevertheless, we see a mind-boggling variety of properties. And this is, of course, due to the differences in the way these building blocks organize themselves. And we call these as phases, right? So what was Landau's key idea? Landau said that the differences between the phases is because they have different symmetries. Okay. Um, Now, it's therefore natural to describe different phases of matter and phase transitions between them in terms of some order parameters, which are actually local quantities, because these symmetries are global. So if every part of the system has the same symmetry, then there's no point in looking at the entire system. You might as well look at a small volume fraction of the system and attribute to it certain symmetry properties, which characterizes the entire phase. So this is the notion of a local order parameter that naturally comes from Landau's idea. And these order parameters then characterize symmetry broken states relative to some more symmetric state. And if you do certain operations, the order parameters will transform non-trivially, especially if it's a broken symmetry phase and you do some operation which is associated with the originally more symmetric phase, then in general, the order parameter will transform. And so everything related to this can be described using group theory. Okay. So you know many examples already. For example, let us consider this honeycomb lattice, and you have a system of spin half particles localized on these vertices of the honeycomb lattice. You can have various kinds of patterns of arrangements of spins, but all these can, in principle, be obtained from some parent Hamiltonian which has spin rotational symmetry. So all these three phases have broken these states correspond to broken spin rotational symmetry because some directions and some patterns are chosen. So these are basically symmetry broken phases, and the parent Hamiltonian might have full rotational symmetry. It also breaks lattice symmetry because the original lattice was a honeycomb lattice, which had its own unit cell and periodicity. But you can see that once a pattern of spins is impressed on it, it does not have the same periodicity as the underlying lattice. So these are typical examples of symmetry broken phases, and you can have more than one in one once you break a certain global symmetry. Landau paradigm has been, of course, an incredibly successful one, and I'll just walk you through some examples. We are now able to, of course, characterize all 230 crystals that are possible in 3D, and also describe, as I showed in the last slide, different types of magnetic orders in lattice systems. Landau theory, this I won't discuss today, but it has been also very successful in understanding critical behavior in the vicinity of symmetry breaking continuous phase transitions. Landau theory also gives you a way to understand the presence of or the existence of gapless bosonic excitations in matter, such as phonons, which is the result of breaking of Galilean symmetry, and also spin waves in antiferromagnets. So these gapless modes arise when some continuous symmetry is broken, and then you can take the resulting symmetry broken state and change it slowly in space and time. And these low energy modes are the Goldstone modes, and they can be phonons, spin waves, and so on. Landau's theory has also had very profound effects on the evolution of concepts in particle and high energy physics. The famous example is the Anderson-Higgs mechanism, or the Meissner effect, if you like, which is closely related to the ideas of how the gauge bosons associated with electroweak interactions, they acquire masses. Like this phenomenon is more or less very similar to the phenomenon of Meissner effect, where the electromagnetic fields are expelled from the bulk of a superconductor. So here, instead of superconductivity, you have the Higgs field, which is the symmetry breaking order parameter. Okay. Now, having reminded ourselves of this Landau paradigm, let's think of what can be, what do we know which is not going to fit in this description. In fact, although I won't have time to discuss, but let me just say it somewhat controversially, that even real life, that is not your textbook superconductors, which are conventional superconductors, can be argued to fall under this beyond Landau paradigm, but I won't discuss this. So in fact, it turns out that these systems have a kind of order called topological order, in particular a Z2 topological order. But let's not go into that. The more well-known example is that of fractional quantum Hall states. So here I have um, okay. Okay. Here, this plot shows on the y-axis the Hall resistance, and also this at the bottom you have these sharp peaks which are associated with longitudinal resistance as a function of the magnetic field. The system is modulation doped heterostructures, semiconductor heterostructures with high mobility. And what you see is, of course, the expected integer quantum Hall effect plateaus. At certain fields, you see these big plateaus which are associated with integer quantum Hall effect. So one such plateau is this one. This, sorry, this one is an integer quantum Hall plateau. But then you see a lot of small plateaus also, which are associated with rational fractions of integers. And so these are associated with fractional quantum Hall effect. And the thing is that if you go from one quantum Hall state to another quantum Hall state, these phase transitions are not associated with any uh, broken symmetries or change of symmetries. So, so you cannot classify these states in terms of order parameters and so on. Although in the beginning, there was an attempt to understand fractional quantum Hall effect in terms of a Landau theory, but that's just not possible. Okay, these don't fit these kind of descriptions. Now, so apart from a longitudinal and Hall resistance, uh, you can measure other properties like thermal Hall response. Thermal Hall response turns out to be in these quantum Hall states quantized as well, and the quantization is in units of some Planck's constant and Boltzmann constants. But the ratio of thermal conductivity to this universal constants, which is written here, gives you a quantity called the chiral central charge of the edge modes. This is a totally independent quantity associated with flow of energy currents around the edge instead of just charge currents around the edge, which is associated with Hall effect. And if you know what is the Hall conductivity, it's not necessary that you will be able to tell what is the chiral central charge. So this is a totally independent property that characterizes the um, uh, quantum Hall state. And here there's a landmark experiment I'm showing you on again these modulation dope heterostructures on a particular plateau of the quantum Hall effect, which is the 5-half plateau. And what you see is that the thermal Hall response, so if you measure the Hall conductivity, it will be 5/2. But if you measure the thermal Hall response, you find that as you go towards progressively lower temperatures, this ratio saturates towards a value of C minus, which is around 2.5. It is half odd integer. If it's half odd integer, you cannot get these weird values from any kind of uh, phase which has excitations that are bosons or fermions or some abelian anions like Laughlin quasiparticles. These have to be some more exotic quasiparticles like Majorana fermions, which are non-abelian anions. So unfortunately, as you go to lower temperatures, you see that this constant departs from 2.5 and starts going to higher values. The authors say that this is because the system is unable to thermalize at low temperatures, so you don't get good results. But then you don't know what to make of it. So the idea is then, can we do something better by not going to very low temperatures, which of course gives us, in the limiting case, the chiral central charge, which is theoretically a very interesting quantity, but instead look at some finite temperature properties, which will then give us some understanding of the underlying topologically ordered state. Okay, so now next example will be what will be the rest of the talk. So if another second example of going beyond Landau paradigm would be that of quantum spin liquids, and the idea comes from Phil Anderson in 1973. He was interested in understanding magnetically disordered ground states of antiferromagnet, Heisenberg antiferromagnets in triangle lattices. Now, in a triangle lattice, if all interactions between neighbors are antiferromagnetic, you can easily see that you cannot please all three bonds. Like if you try to make a singlet between a pair of these, then you can choose some other bond also where it will be singlet, but the third bond will be always unhappy and it will have to be a triplet. So there is inbuilt frustration if you define Heisenberg antiferromagnet on a triangle lattice. So he thought that, well, let us suppose it happens that this ground state of this model is not able to order. It turns out that it does order, but Anderson did not know that. So what he did is he said, let me construct some state which is in general a very disordered state, and it has full rotational symmetry of the original Hamiltonian, and let me look at the properties of such a state. So he therefore constructed this RVB state out of thin air, and the idea is that you take neighbors in whichever way you like. So this is one pattern. You take neighbors which are shown as these ellipsoids, and each ellipsoid represents a bell pair. So it's a fully entangled bell pair. Um, and you then map the entire lattice with these non-overlapping bell pair. Because of monogamy of entanglement, you cannot, if you have two spins forming a bell pair, none of these spins can entangle with something else. So therefore, you can make a timer covering of the lattice in different ways, which is very similar to what you do in benzene. You have multiple choices of forming these uh, resonating bonds, right? So you have multiple patterns you can associate with these singlets, and the ground state is a superposition of all those singlets. So, so now what you have ended up having is an enormous superposition of many body states. And each of these individual components breaks lattice symmetries because it corresponds to some specific pattern of choosing your singlets. But when you take the superposition of all of them, then the resulting state has no symmetries. Okay, it has not broken any symmetries of the original Hamiltonian. So, so then what's so special? It looks like the most boring possible state you can ever write down. But no, it is a very interesting kind of state, and we can associate with this state a different kind of order. Let's see what it is. So first, let's do some local moves. So let's not disturb the entire pattern. Let's take a snapshot and say that wherever possible, I will make moves of this kind. I will take this parallel arrangement of singlets and make it like this slanting arrangement. And wherever such moves are possible, I make local flippable moves. And there could be others also, but this is the standard one. And if I do these local moves, I don't disturb globally the pattern, but locally I might change things. So if I do that, I notice one immediate reality, that if I draw any cut in the system that goes from one end of the system to the other end, cutting bonds, not sides, then I count the number of these bell pairs or singlets that this line crosses. So it will be either odd or even, right? But if you make any local move, I can never change the parity, meaning if it's odd, it's always going to remain odd. If it's even, it's always going to remain even. You cannot change this reality. So this is a global property. It's topological. Okay. So so therefore, you can say that, okay, in this horizontal direction, whatever local moves I make, the parity of how many timers lie on this dashed line is an invariant quantity. And you can draw this horizontal line anywhere and you will get the same answer, by the way. It won't change. Speci yes, you can do very similar things for all kinds of lattices. Yeah. So um, provided that that lattice and that system supports what is called a Z2 topological order. So this lattice, this model can support a Z2 topological order. So so therefore you see this, but lots of lattices can do this. Kagome can do this also. Many others. Square can also do this. So you can do a similar thing in the vertical direction, in the slanting direction also. So along along each of these two fundamental directions, you therefore can associate an odd number or even number, depending on what is the parity of my dimer covering. Okay, so these are like these define now if I make periodic boundary conditions, which we do in condensed matter physics, then this becomes a donut, and these lines become loops which cannot be shrunk. They loop around the holes of the donut. So each loop which is non-contractible is associated with +1 or -1 parity, which is a measure of whether the number of links it cuts, dimer links it cuts, is even or odd. And so you get 4 possible combinations on the torus. In general, if you have another manifold which has multiple handles, which is called genus, then you will be able to make 2G number of independent non-contractible loops. And since each of them is twofold kind of possibilities, you will get 4 to the power of G distinct topological sectors. And these are all part of the ground state. So the ground state is intrinsically degenerate the moment you put it on a closed manifold with a certain genus G. It won't be degenerate on a sphere because G is 0, but it's degenerate the moment you put it on a torus or something with more handles. So, and this degeneracy is robust against arbitrary small but arbitrary perturbations of any kind, because the state had no symmetries to break, so you can put any perturbation. So this topological property is remarkably robust. You can't make it go away unless you completely change the Hamiltonian. Okay, so now how do I look at excitations in such a weird system with robust degeneracy on closed manifolds? Let me try to break one of these dimers. Okay, so I broke it, and now I have 2 spin half degrees of freedom sitting at these corners. Now, once I have broken this, then let us say I look at this dimer, I make it fall down, which means that I pair this particular spin half with this, form a singlet which is horizontal. This one, this singlet. Okay, I form this one. But then what happens is the one which is here becomes isolated, right? So once I have broken a bond, I can make these domino-like things. I can make things fall, and I can move the ends farther and farther away from each other. Um, and and these ends behave like a free excitations. In this RVB state, the spin-ons are called described as being T-confined. What does it mean? It means that once I create them paying a finite energy cost, not infinite energy cost, I can move them around without diverging cost. Meaning, if I move these two ends infinitely far away, then also the cost I will need to pay is going to be finite and not divergent. So in this sense, these spin-ons are T-confined. I can move them freely without extra cost once I create them. Okay, now what is some other kind of excitation I can create? Well, then second kind of excitation, you might have heard this term Wison, is a bit more subtle. So to understand this, what I do is I look at the center of any triangle, and I draw this dash line which goes all the way to the end. So unlike before, this is a semi-infinite line. Okay. And now, so my RVB state of Anderson was an equal superposition of all dimer coverings of this lattice, but I make a different linear superposition of these dimer coverings with phases which are +1 or -1, depending on this number ND, which is nothing but how many bonds, how many singlets I cut in this semi-infinite direction. So here I have cut one dimer like this. So my ND will be 1 for this particular example. Okay. So I similarly, basically I just take this RVB state and choose phases for each components depending on how many cuts, how many dimers I cut in this semi-infinite line. Okay, so what's interesting about this Wison state? Well, now let me do the following. Let me create somewhere around here on one side of the Y zone. I let me break a bond and create two spin-ons, which I introduced in the last slide. And let me move the one of the spin-ons around the loop. So I go on breaking these dominoes and rearranging this alternating pattern necklace. And I bring back my spin on here and highlight it and form the singlet again. So what I've done is I moved a spin on around a Y-zone. But you can clearly see that the moment I do that, the parity of this semi-infinite cut has changed. Here, if you see, I was intersecting, I was intersecting the um, dimer in one place, but now I have two. So the parity has changed, which means the result of taking a spin-on around a Y-zone has changed the sign of my wave function. So these two particles are interacting very much like you would expect, let's say, interaction between a vortex and a Cooper pair. So the Y-zone behaves like a flux or an precursor vortex, but it carries half a flux quantum. Because if it was carrying a full flux quantum and you took a Cooper pair around it, then it would not give you a phase shift of pi, but 2 pi. But now here it gives a phase shift of pi when you take a spin-on around a Y-zone. So the Y-zones are half flux excitations. Such excitations you also can create in chiral P-wave topological superconductors. Okay, so the interaction between the Y-zone and spin-on is statistical. It does not matter how far the Y-zone and spin-on are from each other. The only interaction between them is felt when you take one around the other. Now you might ask, what happens if I take a spin-on around a spin-on? Well, nothing happens. To each other, they are like bosons. And what happens if I take a Y-zone around a Y-zone? Nothing. They are like bosons to each other. But between themselves, they are like semions. Okay, so they are a kind of anion, which is neither a fermion nor a boson, but semions. You take one around the other, you get a phase change of pi. Okay, so you can also show that if you create two closely spaced excitations, which is a pair or which is one Y-zone and one spin-on, the combined entity behaves like a fermion. So you see, I had in the beginning nothing. I had a paramagnetic ground state with no global symmetries, no symmetry breaking. And nevertheless, within that, I'm able to create really weird excitations, some of which are like half flux excitations, some of which are like spin half degrees of freedom floating around freely, and another one is a fermion. So this is what I want to then focus on, that the RVB state is characterized by some very specific patterns of long range entanglement, which means that when I draw these infinite cuts, the parity of the dimer covering is either odd or even, and it's fixed, and I can't change it by any local moves. Uh, I have very weird excitations, fractionalized quasi-particles, which are not there in the ground state. And you can't see it by just looking at these bell pairs, that I will have a system with these kinds of strange excitations. These quasi-particles often have statistical interactions, meaning it's not Coulomb-like interaction, but it's an interaction which is like between a vortex and a charged particle. You have emergent gauge fields. Since I have fluxes, they need to come from some fictitious vector potential, which wasn't there in the beginning, but now it has emerged out of nowhere. Um, and in this case, it gives us a half quantized flux. These are my analogs of abricos of vortices. Okay. And there is robust ground state degeneracy on closed manifolds. These are all ingredients of what Venn called topological order. And this term dates back to 1989. Now, the other examples I gave you, which are beyond Landau, like fractional quantum Hall states and even real world conventional superconductors, also happens to be examples of topological order. They are not quantum spin liquids, but they also are endowed with pretty much very similar features. Okay. So I should not confuse this topological order with topological I hear in other contexts, because the English language might have a word which is used in many contexts, but doesn't mean all the contexts have the same meaning. Okay, so the topological insulators are not topological in this sense. Okay, they represent short ranged entangled phases of matter, and there is the topology there is in a very different context, very different sense. Similarly, the BKT transition was originally also described as a topological transition. It's not, because there is nothing per se topological in this sense about a BKT transition. Some people say possibly the integer quantum Hall effect is also not topological in that sense, although people differ. Okay, so now, how do we? So far, everything has been in pictures, and how do I construct a theory for describing quantum spin liquids? Now, a little before Anderson's famous 1973 paper, Wegener in 1971, while studying some Ising-like models which involve interactions on links and also on faces, uh, he showed that such models can often have phase transitions without any symmetry breaking. And this was later recognized as a phase transition taking place in a Z2 gauge theory. But at that time, of course, no such name was given, and he showed that such transitions are possible that take place without symmetry breaking. Uh, and so this was quite remarkable for that time. So quantum spin liquids similarly are described through some effective field theories most of the time, involving fractionalized matter. Like I showed, spin-ons are my fractionalized matter in the RVB state, and they interact with emergent gauge fields. In our case, the Wisons were the gauge fields. So there is an interaction between the spin-ons and Wisons, which is statistical interaction. So this is a common language that is shared between all forms of topological quantum matter, fractional quantum Hall effect, quantum spin liquids, everything. The language is common. It is gauge theory with, basically, I would say a topological field theory with which represents a statistical interaction between matter and gauge fields. Okay. Now, when I say I'm looking at a U1 spin liquid or SU2 spin liquid or something like that, what do I really mean? It does not mean that, but just by mentioning the gauge group U1, SU2, Z2, the spin liquid is automatically abelian or non-abelian, depending on whether the gauge group is abelian or non-abelian. It's not like that. Uh, by when you name a theory like that with reference to the gauge group, it just means that it means that the gauge fields in the field theory are abelian or non-abelian, as the case may be. Okay, and you really need to do your analysis of the gauge theory to understand whether the excitations in those gauge theories are abelian uh, uh, quasi-particles like the one I showed for the RVB case. Spin-ons and Wisons are abelian quasi-particles, because one beautiful test of an abelian quasi-particle, besides the fact that you can take one around the other and just acquire a phase, um, the another test is that if you take any two abelian quasi-particles and fuse them, meaning you view them very close to each other, then from a distance it looks like a third quasi-particle. Um, there is no more than one possibility. In contrast, if you have an non-abelian topologically ordered state and you take any of the two quasi-particles, there is a possibility that the outcome could be two different things, not unique. So this is the test, and you have to analyze the gauge theory to understand whether the excitations there are abelian or non-abelian. So just by the name you cannot say. The edge excitations of many of these theories are gapless, like the fractional quantum Hall state has an edge mode, which is gapless, and and the bulk is gapped and insulating, right? So, so in such cases, you will further characterize the topological order by properties of the edge mode, such as the chiral central charge or quantum Hall conductivity, and so on. Now, how do I realize these quantum spin liquids? Well, gauge theories can describe quantum spin liquids, but we still need to know what kind of microscopic models gave rise to such phases and what materials I should look for seeing such phases of matter. Now, this is where the challenge is, of course. Some models are theoretically known to have quantum spin liquid ground states, and the earliest one which I like is the toric code model of Kitaev, which has a Z2 spin liquid ground state, pretty much the same as what Anderson wrote. This is, of course, on a square lattice. So this dates back to 2003. And Kitaev made up this model and analyzed it because the anyons are the building blocks of topological quantum computing. So that was the motivation for Kitaev. Subsequently, he also invented this model, the honeycomb Kitaev model, that also happens to have Z2 topological order. But by adding suitable perturbations, you can get some more, other topological phases, like one with non-abelian topological order called Ising topological order, which is basically the same as what you get in the nu equals to 5/2 fractional quantum Hall state in semiconductor heterostructures. So this is uh, like a very interesting model in which I have studied for a while. Then Kagome antiferromagnets. If you take a Kagome lattice and you put localized spin half particles which are interacting antiferromagnetically with each other, then the ground state could be well, there was a big debate whether it's U1 Dirac spin liquid like or Z2 spin liquid like, but now the view is more towards the former, that it's describing U1 Dirac spin liquid. We can also get chiral phases, which are analogs of quantum Hall states uh, by suitable perturbations. And these will have semionic topological order, which means the excitations, when looped around each other, they will give you a phase change of pi. Some spin ice models in 3D systems are also known to have topological order. For example, see this work on quantum spin ice, dysprobium something something, I don't know, uh, Castelnuovo, John Chocker, etc., Roderick Meissner, and so on. Okay, so quantum spin liquids are much more challenging to realize experimentally than fractional quantum Hall states, which are also topologically ordered. Now, the only clean example I know of is on a quantum processor. So this is on a Google quantum processor. There are 31 qubits here. This paper appeared in Science in 2021, and each of these crosses are a qubit, and each of these values I have shown here are they represent what are conserved fluxes. So when you get 1, that means you have a uh, uh, when you have a flux free state there. When I have -1, it means a half vortex state. So the ground state is flux free in this case, and it turns out that the goal of this work was to create the ground state of the toric code model, which Kitaev wrote in 2003. And so there's no Hamiltonian they use to create it, but they use a series of moves, unitary operations, to start from a state with all spin down and create a ground state of the toric code model, which has Z2 topological order. And then they go ahead and do measurements on it and confirm that they have indeed realized quantum spin liquid state with Z2 topological order. Okay, so this has been a remarkable success. Now, materially, the things are more bleak. So some years ago, there was a big splash created when in 2018, the Japanese group of Matsuda, etc., they reported in their measurements of thermal Hall conductivity of a Kitaev material, which is alpha ruthenium trichloride. They said that, okay, if I measure the thermal Hall conductivity at low temperatures, then okay, yeah, you see this thermal Hall conductivity divided by temperature. So as you go to low temperatures, it seems to be saturating towards this dashed line, which if you look at the right hand side, it corresponds to a chiral central charge of half, which is what Kitaev had predicted for the Ising topological order phase, which is a non-abelian phase of the Kitaev model, and it has Majorana zero modes, chiral zero modes on the edge, which will have a chiral central charge of half. So these people said they have discovered this phase in a real material, not on a semiconductor heterostructure. But then this became very controversial because other groups like Ong's group subsequently tried to repeat it, and many other groups like Takagi in Germany, they tried to repeat it, but they did not get any such uh, flattening of the thermal Hall resistance. So what they instead see is that as the temperature is gradually reduced, your thermal Hall conductivity keeps falling monotonously and probably goes to zero uh, at uh, at low fields, at low temperatures. One of the challenges is that the ground state of these materials, although it's a highly frustrated system, the ground state is magnetically ordered. It has zigzag magnetic order in a honeycomb system. And to kill the magnetic order, the experimentalists typically put a magnetic field, which is quite big. It's like 6 or 7 Teslas. Uh, and then by that time, what happens is the quantum spin liquid is also destroyed together with the magnetic order. So you cannot possibly revive the quantum spin liquid using this kind of technique, and which is why most likely this is a red herring, and this phenomenon does not exist, and it's not an example of topological order. So now, as I showed you also in the fractional quantum Hall context, given that it is so difficult to measure the quantized thermal Hall conductivity at low temperatures, could we possibly try to say what is the thermal Hall response at finite temperatures, and from that try to infer if I am looking at a quantum spin liquid, and if so, what type, and so on. And this is where we have been working with my student Avijit Maiti, then postdoc How You Guo in Cornell, and Supir Sachdev, who is in Harvard. And we have a recent publication. I will come to it, but maybe a bit accelerated towards the end. The model is the Kagome uh, Heisenberg antiferromagnet with maybe some perturbations added to break time reversal and inversion symmetry, parity symmetry. Okay, so this is where let me start. This work has seen many collaborators, and I just mentioned my collaborators. The discussions been very invaluable with Shubro Bhattacharjee, Kedar Damle, Yasser Iqbal, which many of you might already know, uh, and Darshan Joshi. We are supported by our funding agencies, and you can see some of the results in these recent papers from our group. Okay, so let me give. Oh, okay, so so as you have perhaps been persuaded by me, or maybe you knew it already, that the measurement of the chiral central charge, although it's a smoking gun signature of the kind of quantum spin liquid you might be looking at, it's very challenging and controversial. And it is even challenging to measure in semiconductor systems, which are usually much better controlled than material systems. So then can the study of the finite temperature thermal Hall response provide a useful signature of a chiral quantum spin liquid? And then second question I want to ask is, given a microscopic model, how do I probe that this model has, given a ground state wave function, can I probe properties of this wave function that will tell me whether this represents a quantum spin liquid, which is chiral? Meaning, can I calculate the chiral central charge directly from the microscopic wave function? So this will be a different approach compared to transport approach, which is thermal Hall. So this is a wave function based approach. So we'll do both. And discuss two examples. One, of course, is the Kagome-Heisenberg system, which I told you about. And the ground state is understood to be a billion chiral spin liquid state. And we'll also discuss the honeycomb-Kitaev system in the non-abelian chiral spin liquid phase. Both these two, I will show how it works. But before I do any of these things, it's perhaps useful to look at the basics of thermal Hall, because it's a slightly weird quantity. It's not only hard to measure, it's hard to understand theoretically as well. So let's start with two-dimensional, two space dimensions and one time dimension. So 2+1 dimensional system. Let's start with something we all agree on, which is energy conservation. Rho of E is the local energy density, and J of E is the energy current density. So now if I'm talking of linear response, which is what thermal conductivity is about, then I can make a gradient expansion of the energy current in derivatives of either the energy or the temperature or so on. So here I make a gradient expansion in temperature. Because I'm in 2D, so let me write down the uh, energy current as a sum of a symmetric part and a skew symmetric part. So here, if I interchange labels P and Q, the sign changes. Okay. So now thermal Hall conductivity turns out to be completely associated with the skew symmetric part of the heat conductivity tensor. So this is where kappa xy is. And if you plug this back into the energy conservation equation, you will find that it makes no contribution to energy conservation equation. Okay. So now a very weird situation arises whether I should view the thermal Hall conductivity as a bulk or a boundary property. So to see this conundrum, let's consider my sample like this in the middle, where I have maintained the sample edges at two different temperatures, T of 0 and T of Ly in the y direction. And these blue regions are reservoirs. These are reservoirs, and my heat can flow from one reservoir to another reservoir while I put a temperature gradient in this direction. So if I just look at the contribution to energy current from the skew symmetric part, which is the thermal Hall part of the conductivity tensor, I can integrate through this cross section, and I find that the total current is basically the difference of two quantities defined on the two edges. So it's some function of a temperature at the top edge minus the same function evaluated at the bottom temperature. So therefore, it looks like an edge property. And so therefore, let's consider the 1D edge. And in 1+1D systems, there is a whole, architecture based on conformal field theory. And one can use those very general ideas to understand what would be the energy and charge transport in a 1D gapless system. So the energy currents in particular are related to the chiral central charge, which is what we are always after, right? So it turns out that this total energy flow in the cross section is simply the difference of two functions evaluated at the two different temperatures on the edges. And it's also proportional to this C minus, which is the chiral central charge of the edge theory. So it shows that, okay, my thermal Hall response, because it measures an edge property, which is the chiral central charge, it is probably an edge property and not a property associated with the bulk of the system. That's not exactly true, because let's consider the following. Let us believe for a moment that the chiral central charge is indeed an edge property and not a bulk property. Then let me just have this sample and I put no temperature difference. Let me put the same temperature on the two edges, and clearly it's in equilibrium, so no heat current can flow. And even if I deform the edge, one of the edges, no heat current can flow. That means the chiral central charge cannot be a property of the edge, and it suggests that thermal Hall conductance is in fact a bulk property. Okay, and furthermore, we also know on general grounds that you create any lattice model in 1D. that is not already a boundary of some larger 2D region. You cannot make any of these lattice models have a low energy description which has a non-zero chiral central charge. So yes, you cannot have you cannot have any 1D system where energy, quantized energy current flows in equilibrium conditions. Okay, so this suggests that thermal Hall conductance is somehow a bulk property, and that is how the explanation came from Spotineko and Kapustin in 2019. And if this is the case, we should be able to obtain chiral central charge from a purely bulk calculation of the thermal Hall conductivity at low temperatures. Okay. Now, what should be the desirable properties of a microscopic bulk formula for the thermal Hall conductivity? Well, one thing, it should not depend on the details of the edge, which we just discussed, and it should also correspond to what you actually measure. It should not be some nonsense quantity. Yeah, it should correspond to what an experimentalist actually measures. So the standard Luttinger-Kubo formulae, which Luttinger uh, uh, obtained in 1964 to describe various thermoelectric linear response quantities, they are not correct for two of the linear response quantities. One is thermal Hall and the other is Nernst. And in both these cases, if you just do the Kubo formula, you will get an infinity. So that means something is wrong. And the reason is that you have to, for both these cases, subtract the Kubo part. You have to subtract a contribution from the, from bound currents which are in the system and which otherwise appear in the definition of the current operator, and they make no contribution to the transport current. So if you want to just associate the linear response with transport current, then you have to subtract from this Kubo contribution this quantity. And it turns out this is also divergent, and but the difference between them is finite and experimentally meaningful. And this quantity M of E is called energy magnetization for thermal Hall. It is very similar to the magnetization you see in magnets. There it is charge magnetization, right? So curl of M gives you the bound electromagnetic current in a material. Similarly, curl of M of E gives you the bound energy current in a material. So this is exactly to be viewed in analogy with the electromagnetic counterpart. So this understanding came much later in 1997, more than 30 years after Luttinger wrote his famous paper. Now, these Kubo formulae are standard and you know them. It involves the standard Kubo averages of the energy currents, and these double angular bracket averages are just, you can obtain them using a Matsubara formulation. Okay, so you would think that, okay, things are done, but as Kitaev pointed out subsequently in 2006, and it was a very mysterious 2-page thing in his appendix of his 100-page Kitaev honeycomb Kitaev paper. So nobody looked at it, and also even if you look at it, it's impossible to understand what he's talking about. So Kapustin and Spodineko then gave a very clear explanation, at least clear to me, of what is really going on. So it turns out that unfortunately, as Kitai found out, the energy magnetization is not a unique function of the parameters of the problem, such as temperature or even interaction parameters and so on. So you cannot obtain it uniquely. So therefore, when you subtract this quantity from the Kubo part, you don't get a unique kind of thing. So the answer depends on what you take for M of E. So it becomes more nonsensical. But the resolution is also provided by them, that let's not talk about the absolute value of thermal Hall conductivity, but talk only about the relative values. Like if you know the thermal Hall conductivity at one temperature, then it turns out you can calculate the thermal Hall conductivity at every other temperature. So you need to have a reference value, which should be given by physics and not by mathematics. So what these guys say is that the temperature derivative of this kappa by T is not only got a Kubo part, but also got a part which is related to the energy magnetization, this quantity tau E is completely uniquely determined in terms of Kubo averages of local terms in the Hamiltonian. So here H of P are the local terms in the Hamiltonian. The Hamiltonian can be written as a sum of local contributions. The J of E PQ is simply the commutator of the local terms in the Hamiltonian. It represents the local energy current. So you do the Kubo averaging on the lattice and plug it back there and everything works. So the problem is then addressed, provided you know on physical grounds what is the thermal Hall conductivity at some temperature. So let's put this to use. As I said before, the thermal Hall conductivity at finite temperatures for this Kagome antiferromagnet is our goal. And as I mentioned quickly already, that the ground state is a U1 Dirac spin liquid. And if I add this time reversal symmetry breaking term, which is called a scalar spin chirality term, it does not break rotational symmetry, but it breaks time reversal and parity symmetries. Then it turns out that the ground state becomes gapped, and it then describes a chiral spin liquid. So you don't need a very large value of J chi. It has to be bigger than arctan of J chi by Jh equals to 0.05 pi. So this chiral spin liquid is believed to be in the same topological class as a fractional quantum Hall state corresponding to nu equals to half Laughlin. So this is very old stuff from Laughlin in 1987. It was written down for the bosonic quantum Hall state, but it turns out that our quantum spin liquid happens to belong to the same topological classification as the nu equals to half Laughlin state. It has a chiral central charge of 1, which means quantum of thermal Hall conductivity is 1. And there is another quantity which is entanglement entropy you can measure. And in all these topologically ordered systems, I did not mention, but if you calculate the von Neumann entanglement entropy, there is a part that depends on the size of or the boundary of the region you have isolated from the rest. But the entropy is actually less than this value which you expect for typically gapped states. The deficit or the amount by which the von Neumann entropy is less than the expectation from a trivial gapped state is called the topological entanglement entropy, and it represents some non-local quantum entanglement in the quantum state, so that even if you integrate out some part of the system, the rest of the system doesn't lose the information of what you have integrated out, but retains certain minimum information which cannot be erased. So it represents 1 qubit of information in the Z2 toric code model, and here it's like a half a qubit. So half log 2 is the topological entanglement entropy for this system. You can calculate the chiral central charge if you are given the bulk wave functions through numerical calculation. For example, you take the spin model, put it on your massive whatever computer, do exact diagonalization or Monte Carlo or do whatever, and you get some estimate for the ground state. You calculate these reduced density matrices with associated with these regions A, B, C, etc., and obtain some entanglement Hamiltonian or what is called a modular Hamiltonian. You take the density matrix and its logarithm. That's a Hamiltonian. And the idea is to calculate the equivalent of thermal Hall current across the region, across any of these boundaries, say between regions A, B, and B, C. So C is the overlapping region, and you are trying to calculate the thermal current between regions A and B. Thermal meaning modular thermal. So it directly gives you the chiral central charge. This is new stuff from Kim in from this general philosophy of using entanglement-based measures of specifying properties of quantum states on the lattice, so you can get chiral central charge in this manner. So if we do this, we find that for our Kagome system, the chiral central charge is indeed 1, as expected for the bosonic quantum Hall state nu equals to half. So we are on the right track, and topological entanglement entropy is also half log 2. So this is exactly half log 2. So therefore, we know what ground state we are looking at. And it is very important to have some numerical check on your analytical formulation, because although the numerics is on a finite size system, and you ultimately need the answer in the thermodynamic limit, if you completely start doing analytical things from the beginning, you may not, you will have to make some approximations which will be uncontrolled, and you will not be able to start with the correct ground state. So guided by experiment, you do the analytic approximations, guided by numerical experiments, that is. And then you can formulate the theory in terms of your quantum fields, and you can get your results in the thermodynamic limit. Okay, so here the idea is to use Abrikosov fermions to represent my spin degrees of freedom. Now, each spin degree of freedom is spin up or spin down. So by introducing two fermions, spin up, spin down, for each spin half degree of freedom, you have introduced uh, too many degrees of freedom, because you can have a zero occupancy, spin up, spin down, and also a double occupancy, which is up down. So you have introduced four possible states in the Hilbert space. You have to kick out two of them. You kick out the zero occupancy and you kick out the double occupancy state. And everywhere you impose this constraint that the total fermion number is 1, after which this representation is exact. Now you put this back in the model Hamiltonian, you will get 4 fermion interaction terms. So you have to do some mean field approximation, and this is where you are guided by numerics. So a wrong mean field approximation means you will be looking at something else. So you do the correct mean field approximation, and what you get in the end is a tight binding model with some interactions. Now, so the band structure of the tight binding model is like this. You get a bunch of bands which have non-zero Chern numbers. Because in this Kagome lattice, I get 6 bands. So I have these 6 bands shown here, and the Chern numbers of these bands are all like distributed in the following pattern: -1, -1, 1, -1, 1, 1. And the ground state corresponds to exactly half filling. So this is familiar to people who work with bands. So it looks like a conventional topological insulator right now. Okay. So now what we do is to get a description of the low energy physics near the Fermi level, we integrate out these distant bands. But the total chirality of the distant bands is non-zero. So therefore, what happens is when I integrate out these distant bands, I get a gauge theory of fermions, Dirac fermions in these two light bands, and interacting with some Chern-Simons term, which is a topological interaction describing statistical interactions between semons. So don't go into like, ignore my jargon, but you get some gauge theory of two-dimensional quantum matter, which is fermions, interacting with gauge fields whose action is a Chern-Simons theory. There is a Maxwell's term also, which I have not written. And what you now do is you try to calculate the thermal Hall conductivity using Kapustin's prescription. For that, you will need the energy current operators. So you can easily do that in field theory. You can get the energy momentum stress tensor, T mu nu, and it turns out that the thermal Hall conductivity is related to correlation functions of the stress tensor. So T mu 0, T rho 0. In particular, you need the skew symmetric part of this correlators, because thermal Hall response is related to the skew symmetric part of linear response thermal conductivity. So you can get the both the Kubo part and the energy magnetization parts very easily. It's important to take the limits in the appropriate order. So the diagrams are standard. Many of you have seen the diagrams that appear here in these two figures from your experience with superconductivity. So there is no small parameter in the problem, unlike QED, which has a small parameter, which is my fine structure constant. 1 over 137. Here there is the coupling constant is 1, so I cannot do anything. So what people do is they introduce very large number of copies of the model, which is called a large n approximation. So then I treat 1 over n, where n is the number of copies or number of fermions in the system. Uh, I treat 1 over n as a perturbation parameter, and that helps me organize my diagrammatic expansion. Otherwise, there's no way to do diagrammatics. Okay, the leading order contribution comes from free fermions, which is from band theory, and these are shown here. And the second diagram actually makes no contribution. So we have just what this diagram is what exactly you would get from band theory. These other diagrams are 1 over n order smaller than this, and they represent three types of diagrams which many of you recognize in superconductivity as the density of states correction to conductivity, the Markey-Thompson correction to conductivity, which is like a vertex correction. This is like a self-energy correction, and this is the Aslamazov-Larkin type of diagram, which has two gauge fields. Now, these dashed lines in our theory, because of gauge invariance, you have to include all possible processes. So not only the fermion triangles, but also things involving the gauge fields. Okay, so once you do this, everything becomes very systematic. It turns out that the only important contribution to worry about is the Aslamazov-Larkin contribution in this gauge part. Sorry, I'm ending soon. Um, so so this is the Aslamazov-Larkin contribution. These two turn out to be very unimportant. So I will only focus on Aslamazov-Larkin when we do gauge contribution. So let's look at what the free theory tells you. If you look at just the band theory, then you can actually calculate very easily the thermal Hall conductivity, and you find that at low temperatures, it gives a wrong result of chiral central charge equals to 2. And this is because you have ignored the contribution from gauge fluctuations. The behavior at high temperatures is basically a constant. So it means the thermal Hall conductivity saturates to a constant value at very high temperatures in a pure band theory. So this is with an infinite spectrum. If I put a finite bandwidth, which is a real tight binding model, then the thermal Hall conductivity will go to 0, like 1 over t squared. And in particular, this ratio k over t goes to 0 like 1 over t cubed. So if you want to make a test of thermal Hall conductivity, your calculations are correct or not, look for the 1 over t square tail at high temperatures. But this is wrong at low temperatures because this is not the right result. We expect a chiral center charge of 1. So how do we get that? Well, we have to now look at the contribution from the Aslamazov-Larkin processes, and they give you further correction. Now, this some progress in this regard was done by Subir and his then PhD student Guo in 2020. And what they did was to ignore the fermionic excitations in these triangles and just replace it by a temperature independent vertex, which is shown on the right. This is actually valid at low temperatures. So if you do that, then this becomes a pure gauge theory. It has no matter in it. And then you can add the contributions of the pure gauge theory and the pure fermionic non-interacting theory together and get some results. This works at low temperatures. In fact, you will get, if you look at Go in 2020, you will, this blue curve, you will get a correct chiral central charge of 1. Now, what we realized is that this is not good enough if you want to go to higher temperatures. So you will have to look into those triangles and realize that it contains fermionic matter, which has a finite gap. So it has a temperature dependence of its own, and you have to take that into account while calculating thermal Hall. So this is what we did, and the end result is, after a lot of calculations, that the thermal Hall conductivity goes logarithmically. The correction, the Aslamazov-Larkin corrections grow logarithmically in temperature. So at some point, they will be comparable to the pair free fermion contribution. And that's when my perturbation theory breaks down and I should not do it. But in a big window of temperatures above the spectral gap and below this bandwidth of my type banding model, which is capital M, I will be able to get a correct description. So I can get access to the quantum critical regime in that sense. So these finite temperature results are our central contribution. I want to just flash the results for the Kitaev case because I'm about to end my time now. I can do the same calculation for the honeycomb Kitaev model, which is this. In addition, I have added a magnetic field perturbation in the 111 direction, which is Zeeman-like. And I've also put another kind of time reversal symmetry breaking term, which involves 3 spins. It's very similar to the scalar spin chirality perturbation we put in the Kagome case. So now with these parameters, I play around. So at low fields and a large K, I will have a non-abelian quantum spin liquid state, which is what Kitaev predicted. And at high fields, I will have a trivial paramagnetic phase. So this is the nature of the phase transition. So if you take this Kitaev model, you can choose various parameters so that you are in the topologically ordered phase. You can do some uh, calculation of directly from the microscopic ground state wave function. We use exact diagonalization. We went up to system sizes up to 30, and uh, we have to use all possible symmetries to reach these sizes because the Hilbert space is 2 to the power of 30, which is a billion, right? So so these chiral central charge is expected in the thermodynamic limit to be zero 0.5, and topological entanglement entropy is also log 2. We can similarly get the thermal Hall response from transport measurements, and this transport measurements also gives you the expected half quantized thermal Hall conductivity here, this solid line at low temperatures. So this is where I want to end. Um, uh, if you are at high fields, you can compare your numerical results or analytical field theory results with spin wave calculations. So you can expand in Holstein-Primakov approximation. You can do a spin wave expansion, and the non-interacting spin wave uh, approximation already gives you some idea of what the thermal Hall response looks like at high fields. And you can see that I get pretty much similar looking curves at these high fields. The values are also comparable, the peak values, but the position of the peaks are somewhat shifted, probably the result of approximation made in the spin wave calculation. But at low fields, when I have Ising topological order, my magnons or spin waves are no longer good quasi-particles, and I'll get garbage. I should not do it. So then you have to do numerics or you do field theory. Don't do spin waves. So that's where I want to end. And thank you. Thanks a lot.
Yeah. Thank you so much, Vikram. Thank you. And now we have time for some questions.
Yeah. Okay.
Let me apologize for sort of stupid question. Yeah, but could you please explain us the structure of the total multi-electron wave function in RVP state or your spin liquid or topological? I will just add a few words. We know from textbook some simple examples. Well, like Hartree-Fock, we have just Slater determinant. Yes. In PCS, we have anti-symmetrized product of pair functions, which are the same. Yeah. What is here?
Okay. Yes, I think I can answer it. Wait. So I need to go back to the cartoon picture I drew, and it will become hopefully clear if I look at it. So if you see Anderson's construction of the RVB wave function, it is as follows. So you, yeah. you look at any of these. So each of these ellipsoids is a spin singlet. Each of these ellipsoids is a spin singlet. It's antisymmetric. And I take a product of these singlet wave functions. It's just a direct product. Okay. So this represents just one component of the state. Then I take a superposition of this with another arrangement of singlets. So I now choose some of the ellipsoids to be different, and I again write a product state of these singlets once more. So it's not a Slater determinant. And similarly, you go on creating this massive superposition of each involving product states of singlets, and each component has exactly the same weight and the same phase. So this is Anderson's fiat. I mean, he wrote down this state. It's I know of only one model, which is the Roxar-Kivelson model, which has this as the ground state in some parameter regime. We know of no other models for which this particular state is the ground state.
As a set of BCS condensates.
Yes, yes.
Many of
Yes,
them. And
yes.
you sum up.
Exactly.
Yes.
Exactly. It is very much like that. In fact, those people who believe that high temperature superconductivity is born out of a quantum spin liquid, they would take this as the starting point. They would say that this is already pregnant with superconductivity. It is already formed Cooper pairs, but they cannot move. These Cooper pairs cannot move because everything is blocking everything else. But now I put some holes in the system so that I have space to move. So now these Cooper pairs suddenly at some point become superfluid because they are bosons. And so this is the mechanism of superconductivity from that perspective. And you don't need a phonon mechanism. So you condense these Cooper pairs. Yeah, so you are right.
All right, good. Other questions? So Yushin-Hai, please.
You present here the short range RVB. Are there any form which present long range RVB in mathematical form?
Analytically, they will be very hard to study, but Anderson's original proposal for high temperature superconductivity was actually a long range RVB, so that you can form singlets between arbitrarily separated spins, and then each snapshot is as a product of these Cooper pairs, some of which could be formed of electrons quite far away from each other. However, those are like impossible to study analytically, so we tend to work with these.
Maybe not to study analytically, but at least to present the class of function which explicitly presents such a long range order class of function.
Yes, unfortunately, I don't know, but there has to be there has to be some topological classification of those long range RVB states also. Yeah.
All right, thanks. Urut. Yusuf still had a question, right?
Thank you very much for this very nice talk. I have one simple question. In 1+1 dimension in the Gauss regime, you have central charge which is always equal to 1. In your case, it is universal and it is 1/2. Is there any physical reason behind this? And could you elaborate on this? Thank you.
Okay, so let's yeah. So there are two things. One is the central charge of a 1+1D conformal field theory. The central charge is basically the sum total of the left central charge for the left movers and the central charge for the right movers. So it's the mean of that in a way. So that is often 1, but it could be some rational fractions also, depending on the type of conformal field theory you're looking at. For example, even if you take a transverse field Ising model in 1D, at the gapless point where the ferromagnetic interaction equals the transverse field value, the gap closes. That is described by a 1 plus 1D conformal field theory with central charge half. So there are examples we know. There are other more exotic models with other rational central charges. In my case, I gave two examples. One where the central charge, so I'm talking of a different central charge, which is the chiral central charge, which means either the left or the right. So not the average of the two. So now this chiral central charge cannot be non-zero for any freestanding 1 plus 1D model. That is due to some field theory arguments related to some gravitational anomalies or something like that. If you have, on the other hand, the system, 1 plus 1D system on the boundary of a 2D system, then it's possible to have CFTs on the edge which have non-zero chiral central charge, like you see in quantum Hall effect, both integer and fractional. So these are because those theories intrinsically have anomalies, and for integer quantum Hall effect and all abelian phases, the chiral central charge is an integer. For non-abelian phases, like the nu equals to 5 half fractional quantum Hall state, and also the Kitaev isotropic Kitaev state phase, you have a chiral central charge of half. This is different from transverse field Ising model, where the total central charge in 1D transfer field Ising model is half. This is a chiral central charge, which is half. So it will show up in thermal Hall conductivity quantization, for instance. Just another property characterizing the quantum Hall, the quantum spin liquid. Yeah.
Okay, thank you.
Okay, thanks a lot. And the very last question. Yeah, please.
First of all, thank you for very interesting lecture. And my question is, what is the naturally simple way to determine the topological order in the system? Because there are many ways to do it. For example, analyze the symmetry of ground states of Hamiltonian, or using like topological invariance or something somehow. What way is the best or natural one to determine the topological order? Thank you.
Okay, so the best way, if you are doing a numerical calculation or some analytical treatment, would be to calculate the scaling of the entanglement entropy, and extract this quantity gamma, which I showed, which is the topological entanglement entropy. So your entanglement entropy, von Neumann entropy, or even Renyi entropy would be smaller than what you expect for a non-topological ground state. It will be generally lower by a constant value, and that represents extra information you have about the region you have traced out. So this can be calculated numerically quite reliably if you have a good idea of the numerical wave function. You can also, as I showed, numerically calculate the chiral central charge. These two properties are very important characteristics of quantum spin liquid, or in general any gapped topological phase, including fractional quantum Hall effect. Regarding gapless quantum spin liquids, which I did not discuss, those are very hard to analyze numerically, like with all gapless systems. Experimentally, if you are interested, I don't know of smoking gun tests except thermal Hall for the quantum spin liquids. For the quantum Hall case, which is electronic quantum Hall, you can also measure quantum Hall effect. And if you see fractions, not integer values, that usually is a topologically ordered state, and there is extensive understanding of those topological phases. So I hope I answered it. Yeah.
Yeah, I believe so. Yeah, thank you so much. We are perfect in time. Thank you.